Today, I'd like to talk about 6 tips for getting more accurate flow measurements. The tips are going to focus on problems such as baseline error, non-perpendicular or turbulent flow, and flow variability. The root cause of baseline error is eddy currents. Eddy currents are loops of electrical current that are induced within a metal conductor by a changing magnetic field. These currents are induced, for example, in the metal housing that encloses the magnet. To perform an MRI study, one is constantly changing the magnetic field, so eddy currents are a constant problem. The faster you image, the faster the magnetic field is changed. This causes larger eddy currents and leads to bigger problems. So how do eddy currents affect flow measurements? Well, they make the magnetic field gradients that are used for measuring flow imperfect. You can see that here on this slide. On the left is a curve that shows what happens when you apply a magnetic field gradient for a short time. The graph should look like a trapezoid. Instead, if you zoom in, you can see some of the corners of the trapezoid are rounded. These imperfections cause a baseline error when trying to measure flow. You can see the result here on the right, where the graph shows blood flow versus time. The way you quantify the blood flow is you integrate the area under the curve. Eddy currents cause the curve to shift up or down so that the area under the curve changes. In this case, the curve is shown shifting upwards, and the additional flow is shown here in green. It turns out that flow measurements are very sensitive to even small baseline errors. I'm going to introduce a term here called VENC. It stands for velocity encoding. Anytime the scanner measures flow, you need to set a VENC, a velocity limit, below which you will get no aliasing. This is analogous to the Nyquist limit that is used in ultrasound and echocardiography. As shown in this example, if you set the VENC to plus or minus 200 centimeters per second, a 1% velocity error can create a 20 milliliter flow error in a 3.5 centimeter diameter vessel. For a patient with an 80 milliliter stroke volume, that 1% velocity error causes a 25% error in flow. It turns out that these errors are even bigger as the cross-sectional area of the vessel increases. You can see that in the graph here. As the vessel size goes up, you can see the flow error increases. So the first tip is, if you want to measure flow in an aneurysmal vessel, you're better off measuring it before or after the aneurysm when the vessel has a smaller cross-sectional area. You can actually see these baseline errors if you put a bottle of water in the scanner and try to measure flow. This bottle of water is sometimes called a phantom. Since there is no flow in a bottle of water, the velocity image should look uniformly gray. But in the image on the right, the velocity image shows the bottle of water is darker at 6 to 7 o'clock compared to 12 o'clock. In other words, the water appears to be moving at different velocities within the bottle, which clearly is not the case. It also shows that often the errors are worse the further off-center you are, which leads me to the second tip. Try to measure flow as close to the center of the bore as possible. Now you might say this is impossible, that you don't have any control over where the vessel is in the image. While this may be true in the imaging plane, you do have control in the slice direction. For instance, just acquire one slice at a time and make sure the scanner moves the imaging plane to the center of the magnet. If you prescribe more than one slice at a time, then while the center slice may be centered, the other slices won't be. Let me show you an example. Here's an example where 3 slices were acquired through a phantom. The graph here on the left shows what the flow is in the phantom for each of the 3 slices. And what you can see is the blue curve represents an ROI from the center slice, whereas the red and pink curves represent an ROI from one slice on either side. And what it shows is indeed the center slice gives you less of an offset or baseline error. You may recall that I said earlier that eddy currents are worse when one changes the magnetic fields more rapidly. This means that baseline error will change with the acquisition parameters. So for example, this slide shows the baseline offset is worse as one tries to scan faster. Again, the red curve shows when a receiver bandwidth is at 31 kilohertz. That's slower scanning. As we go faster, 62 kilohertz receive bandwidth, and to pink at 125 kilohertz, you can see the baseline offsets are progressively getting worse. Similarly, smaller VENCs require larger gradients and can cause larger baseline errors. This is the next tip. Each scanner is different. I suggest you put a bottle of water in your scanner and determine a single set of imaging parameters that results in an overall small baseline error. This brings me to the next point. A common problem that users encounter is how to set the VENC. Many users are under the false impression that small differences in this parameter are important. This is usually based on books and papers that make statements like this. For optimal noise performance, the VENC should therefore always be selected as small as possible. While this statement is true, there are considerations other than noise performance that should be considered when setting the VENC. In fact, noise performance is one of the least important considerations because the noise in flow images is often much lower than in other images, because flow images typically have very bright blood, and they also tend to have poorer spatial resolution, which means their signal to noise is actually higher. In fact, small VENCs often have detrimental effects. Other than the obvious fact that they can result in aliasing, they can lengthen the repetition time and thereby decrease the temporal resolution. They can also lengthen the echo time and make the flow values less accurate due to blood acceleration. I'll talk more about that later. Low VENCs can also cause greater baseline errors. The next tip is that VENC values should be set comfortably larger than what you could possibly need. As a rough guide, that generally means 100 centimeters per second for venous flow or atrial shunts, 200 centimeters per second for normal arterial flow, and 550 centimeters per second for arterial stenoses. With this scheme, intermediate VENC values are unnecessary. Given that the baseline is always affected by eddy currents, we need some kind of method to try to correct for the baseline error. Doing nothing is not an option. For other places in the body, like the neck, one can place a region of interest in the stationary tissue that surrounds the vessel, and that can be used to calibrate the baseline. You can see that here in blue. The problem is that in the chest there is no stationary tissue that normally surrounds the great vessels. So in the past, people have placed the background region of interest in more distant stationary tissue, like the chest wall and the liver. The problem is this method gives very inaccurate results because these regions of interest aren't close enough and don't surround the vessel. Here's an example where the flow in the aorta is 93 milliliters with no correction. Now, if I put a background region of interest in the anterior chest wall, that 93 milliliters goes up to 97 milliliters. But if I chose to put it in the liver, it goes up now to 109 milliliters. And if I put it in the lateral chest wall, it goes down to 20 milliliters. So what do you believe? Clearly, this method is very subjective and can lead to very inaccurate results. Well, it turns out that there are some other options which are better. One is something that's been out for a few years called autocorrection. It actually recognizes the fact that there's no stationary tissue next to the aorta, but it looks at the more distant stationary tissue and interpolates back to the central aorta to estimate what the baseline should be there. Now, an important limitation of this technique is that you have static tissue that surrounds the aorta, so you can't have a small field of view or you'll get phase wrap, and that can make the algorithm fail. You also can't have large amounts of metal artifact where you're missing a lot of stationary tissue. A more robust but more cumbersome solution is the phantom correction. And what that is after you've made your flow measurements in the patient gets off the table and then you put in a phantom or a bottle of water, and the software will then go ahead and make the measurement in the bottle of water, figure out what the baseline offset is, and then subtract it from the vessel. Unfortunately, this takes extra time and is not very popular to do. Another problem with getting accurate flows is if the blood flow is turbulent. Even mild turbulence can be a problem. Let me explain why this is. Here's a schematic showing two water molecules. One is stationary, right here. The other one is moving inside a blood vessel, right here. The way the MRI scanner measures blood flow is a magnetic field gradient is turned on. In this case, both sets of hydrogen nuclei experience an increase in the magnetic field strength. They're both located in this position, and here you can see a higher magnetic field strength. And as a result, because the rate at which these nuclei spin is directly proportional to the magnetic field strength, both nuclei speed up. In this case, I've shown 65 degrees. Then what happens is time elapses, and what happens during this elapsed time is the stationary water molecule stays where it was, but the one that was in the blood vessel moves. And then another gradient is applied in an equal but opposite manner, so that the stationary water molecule, those hydrogen nuclei, actually experience a lower magnetic strength and slow down, whereas the hydrogen nuclei that moved again experience a higher magnetic field strength. So as a result, if we look at where these nuclei are, these hydrogen nuclei that were stationary are back at 0 degrees, where they started from, but the hydrogen nuclei that moved in the vessel actually changed phase by 130 degrees. And the scanner is able to calculate a velocity based on the change in phase, so this measurement here, divided by how much time it took for these molecules to move that amount. However, this only works when the spins are moving at constant velocity over delta t. In cases where blood flow is turbulent and there is acceleration or jerk, the velocity will be incorrect. And as a result, it is important to avoid trying to quantify flow when the blood flow is turbulent. So what are the practical considerations when measuring aortic flow? There are a number of different places one can make the measurement. They each have their advantages and disadvantages. Location 2, which is at the sinotubular junction, is a great place to measure aortic regurgitation, but it's not such a good place to measure forward flow because flow values can be affected by turbulence from the aortic valve, even in the absence of aortic stenosis. This graph here on the right shows a correlation between, in this case, pulmonary artery flow and LV stroke volume, and you can see we have a very good correlation. And here's aortic flow measured at the sinotubular junction versus LV stroke volume, and you can see the correlation is not so good. And in the people where there was poor agreement, we found higher aortic velocities and higher stroke volumes. So the ingredients, if you will, for more turbulent flow. Here's an example of a patient with a bicuspid aortic valve and no aortic stenosis. You can look at the flow values slice by slice as we travel from the outflow tract through the sinotubular junction. And what you can see is the flow values here in red and blue and pink are about the same, 130 to 132 milliliters per beat. But then once we get past the valve, they drop to 112 milliliters per beat and then 94 milliliters per beat. And you can see that here, that these two slices where you're past the valve and at the sinotubular junction are giving you artifactually lower flows. The distal ascending aorta, location 3, is the most robust for quantifying forward aortic flow. The LV outflow tract can also be a good place, here position 1, provided there is no turbulence from the LV outflow tract if there's, for instance, LV outflow tract obstruction. Location 2 is best for quantifying aortic regurgitation because it is closest to the valve and there's no turbulence in diastole. Finally, it is important that the flow measurements be made perpendicular to the direction of flow, or the results may be inaccurate. My final tip for getting more accurate flows is a simple one. Many patients have variable flow values either due to actual changes in flow, such as when they have arrhythmias, or for technical reasons, such as bad gating. My recommendation is to acquire several flow values during each cardiac MRI exam to try to understand the variability of the flow values you're getting. We typically make 5 flow measurements for each exam. If all the flow values are the same, then you can count on there being an accurate reflection of what is going on physiologically. On the other hand, if the values are not concordant, then you need to take the measurements with a grain of salt. To summarize, here are your 6 tips for getting more accurate flows. Choose a location where the vessel is not enlarged. Make the flow measurements near the center of the bore. Choose acquisition parameters that minimize baseline errors. Use a good method for baseline correction. Avoid non-perpendicular and turbulent flow. And finally, make multiple flow measurements. Thank you very much.